So, next is disadvantages of low power factor, right. So, what are the disadvantages? For a 3-phase balanced system, for example, say if load is PL, say some terminal voltage is V and power factor is cos phi, then load current is given by IL is equal to PL upon root 3 V cos phi. This is equation 35. Now, if PL and V, if both are constant, say, then the load current IL is inversely proportional to the power factor. If PL and V both are constant, that is phi constant, cos phi is constant. If cos phi is low, then IL is large. If PL will be constant and cos phi is low, so IL will be large. The poor power factor of the system has the following disadvantages. So, this is for first couple of hours, this is for your some general ideas of the system or power factor. Now, number 1, the rating of generators and transformers are inversely proportional to the power factor. Thus, generators and transformers are required to deliver same load, that is real power, at low power factor if power factor is poor. Hence, system KVA or MVA supply will increase, right, because if power factor is poor, although to supply the same real power, that KVA or MVA supply will increase because reactive power will increase, right. Now, because hence many other things are associated with that, later we will discuss. At low power factor, the transmission lines, feeders or cable have to carry more current for the same power to be transmitted, because of poor power factor, more your what you call reactive power has to flow to the line, right. So, thus conductor size will increase because current will increase, right. Therefore, ampacity of the conductor will increase, conductor size will increase. If current density in the line is to be kept constant, right, therefore, at low power factor, the transmission lines, feeder or cable have to carry more current for the same power to be transmitted. Thus, conductor size will increase. If current density in the line is to be kept constant, right, therefore, more copper is required for transmission line, feeders and cables to deliver the same load, but at low power factor. That means, at low power factor, current will be high, right. Therefore, the conductor size will increase, right. Therefore, this if conductor size increases, is you need more volume of the copper will be required, right. So, that way it is I mean explained, right. If it is now conductors are ACS are conductor, right, all these things are there, but volume of the conductor will increase, right, for the same load to be transmitted. Therefore, power factor is poor power factor has lot of disadvantages, right. Number 3 is power loss is proportional to the square of the current and hence inversely proportional to the square of the power factor. So, more power loss is incurred at low power factor and hence poor efficiency. That means, transmission line efficiency will be poor because line current will increase and therefore, power loss will increase, right. So, this is number 3, and number 4 is low lagging power factor result in large voltage drop, right, which result in poor voltage regulation. Hence, additional regulating equipment is required to keep the voltage drop within permissible limit, right. So, all these are the disadvantages of poor power factor. We always want that for any system, it should operate at unity power factor. Perhaps in reality it may not be possible, but we want that, right. So, electric utilities insist the industrial consumer, particularly industrial consumers, to maintain the power factor 0.8 or above, right. Because if industry, they have different parts of tariff, right. Sometimes they charge on kilowatt rate, you got kilowatt demand, KVA demand, they have 2-part or 3-part tariff, right. If your power factor is poor, then KVA demand will be more, then more tariff, based on KVA demand also they charge, utilities they charge from the industry on KVA demand. That is why they have to improve the power factor, right. So, the power tariffs are devised to penalize the consumers with low lagging power factor and force them to install power factor correction devices, for example shunt capacitor. That if your power factor is poor, you will draw more kVA from the utility, right, and in this case you have to pay more money because they have a two-part tariff. They charge on your maximum kVA demand also. If your kVA demand is less, if kVA demand is less means power factor is better, right. If kVA demand is more means power factor is poor. So that's why they will always try to see that kVA demand is less, because one part of the tariff is based on their kilovolt ampere or kVA demand, right. Now various causes of low power factor. Most of the induction motors operate at lagging power factor, right. The power factor of these motors falls with the decrease of load. This is one reason. Then second one is occurrence of increased supply main voltage during low load periods, right. The magnetizing current of inductive reactances increase and power of the electrical plant as a whole comes down, right. It is actually a power factor, right. The third one is very low lagging power factor of agricultural motor pump set. Agricultural motor pump set, they operate at very low power factor, right, I mean very poor, and because of that also sometimes agricultural motor pump set also you will find that frequent burning of the windings, fault will be there, right. Then arc lamps, electric discharge lamps and some other electric equipments operate at very low power factor, right. Arc and induction furnaces operate on very low lagging power factor. So these are some of the equipment, they operate at very low lagging power factor, right. These are some of the, so your what you call the there are common reason for low power, various cases for low power factor, right. Next we will take another example, right. A peak demand of a generating station is 90 megawatt and load factor is 0.6. The planned capacity factor and planned use factor are 0.5 and 0.8 respectively. This planned capacity factor and planned use factor earlier we have discussed, right. Determine daily energy produced, B installed capacity of plant, right, and C that reserve capacity of plant, and D utilization factor. These four things you have to obtain: daily energy produced, then installed capacity of plant, then reserve capacity of plant, and D utilization factor, right. So solution, maximum demand is 90 megawatt, this is given, maximum demand is given 90 megawatt, right, and your load factor is given 0.6, that is also given. Therefore average demand is equal to maximum demand into load factor. So average demand is equal to 90 into 0.6, hence 54 megawatt, this is the average demand. Now daily energy produced is equal to average demand into 24 hours in a day, so 24, that is 54 into 24, it is equal to 1296 megawatt hour, right. So from equation 3 now, plant factor is equal to, this is part B. Part B you have to find out installed capacity of plant. Now plant factor is equal to annual energy produced, right, divided by maximum plant rating into the time. Plant factor is given 0.5, it is given, right, and actual energy produced already you have got it 1296 megawatt hour, this also you have got it. Therefore maximum plant rating, it is 1296, right, divided by 0.5 into 24 is equal to 108 megawatt. This is the plant rating. Therefore plant rating is equal to installed capacity. So installed capacity is 108 megawatt, right. Now part C, reserve capacity is equal to installed capacity minus peak demand. Installed capacity is 108 megawatt and peak demand is 90 megawatt, that is already given, peak demand is given 90 megawatt, right. Therefore 108 minus 90, that is 18 megawatt, right. And from equation to utilization factor, right, UF is equal to maximum demand of the system divided by rated system capacity. Maximum demand is 90 megawatt, and this is rated system capacity, that is installed capacity, that is the same thing, that is the rated system capacity 108 megawatt. So utilization factor is 90 divided by 108, that is equal to 0.833, right. So this is the general. So some examples, some 4-5 examples, standard examples we have taken for this, that introduction part, altogether the structure of power systems and few other aspects, right. So from this some we have some general ideas regarding the different terminology regarding transmission, generation, transmission and distribution systems, right. Plus we have seen that relationship between load factor and loss factor, that how direct it is not possible, but some relationship has been established, and those formula for relationship between loss factor and load factor are commonly used, right. And some general ideas you have regarding different type of load factor, loss factor, utilization factor, coincidence factor, then demand factor, then diversity factor, all this terminology in the beginning we have used, right. And after this we will start for this thing is that your what you call that resistance, inductance, capacitance of the transmission line. First we will see that resistance, then we will see that your what you call inductance, and then we will see the capacitance of the this thing transmission line, right. So these are the common thing for this power system course. And so first thing is that we will start from the this thing, that resistance and inductance of transmission lines. After that we will see that your what you call that capacitance. So basic purpose of a transmission network is to transfer electrical energy, that we have seen this thing, we have the previous thing, from generating units at various locations, right, to the distribution system which ultimately supplies the load. So transmission system actually transmit power from the generating to the consumer distribution side, right. So transmission line also interconnect neighboring power utilities, just we have discussed before, right, which allows not only economic dispatch of electrical power within regions during normal conditions, but also transfer of power between regions during emergencies, right. So this is that interconnected operation we have seen before, that how actually different areas are interconnected, how it will be useful, that reasons for interconnections, right. Basically a transmission line has 4 parameters: resistance, inductance, capacitance and shunt conductance. These 4 parameters are there for transmission system, transmission line. So generally your resistance is the important part of a transmission line, because it consumes its copper loss I square R, right, it that is the major thing. So resistance is an important, and for transmission system, that different for different your what you call different voltage levels, the different type of conductors are used. Particularly for transmission system, if I can recall all sort of thing, that you will find the conductors names are on the name of the animals, like zebra, then tiger, right, then your wolf, that different name of the different type of animals, right, those conductors. And it depends on the voltage level, different conductors has different resistance per ohm per kilometer, and as well as that reactance, right. So while of course it has a bundle conductors are there, double circuit lines are there, different type of when you have seen that high tension transmission line, you have seen in each phase may have 2 or 3 or even more conductors, bundle conductors are there, sometimes single conductors are there in each phase, right. So all these things, your this resistance depends on the your of course depends on the type of the material whatever you use for the conductor, and its cross sectional area, because we know R is equal to resistance is equal to rho into L upon A. A is the cross sectional area of the conductor. So this when if I recall correctly, the resistance, of course, it depends on the cross section area. If you have a very large, if the cross section of the conductor is large, right, then R is equal to rho L by A, so naturally resistance will be lower, right. But in the case of reactor, resistance vary in a very from 33 kV to 400 kV transmission line, say, resistance are different. They are totally different. I mean, quite lower value to higher value to lower value, from low voltage to high voltage. Whereas in the case of inductance and hence the reactance, whenever we try to compute, I was making some computation, I found that reactance part generally with voltage level from 33 kV to say 400 kV, reactant parts roughly it will find it varies in between 0.26 ohm per kilometer to 0.34 or 0.35 ohm per kilometer, right. This way more or less it varies, right, whereas resistance variation is much more for your transmission line, right. So later we will try to see. So this shunt conductance, actually we have told three parameters for resistance, inductance, capacitance and shunt conductance. So shunt conductance actually accounts for leakage currents flowing across insulators and ionized pathways in the air, right. So but these leakage currents are negligible. These leakage currents are negligible as compared to the current flowing in the transmission lines. So this shunt conductance thing we will not consider for our study, right. But for the sake of clarification, basically for transmission line we consider four parameters. So resistance, inductance, capacitance and your conductance, right. So it is for across the insulator, it may happen and ionized pathways in the air, right. But the series resistance causes a real power loss in the conductor, because I square loss, R loss will be there. So resistance of the conductor is very important in transmission efficiency evaluation and economic studies, because if resistance is more, then power loss will be more, right. So this is very important. Second thing is, the power transmission capacity of the transmission line is mainly governed by the series inductance X, right. For a transmission line, if you see that R by X ratio is quite small, or other way X by R ratio is quite high, right. Therefore, this your power transmission capacity of the transmission line is mainly governed by the series inductance, right. And third point is the shunt capacitance causes charging current to flow in the line, right, and assumes importance for medium and long transmission line, long overhead lines. If it is a cable, then perhaps at low voltage level 11 kV also you have to consider the charging current, you cannot ignore, right. But for overhead transmission line, this charging your shunt capacitance up to 33 kV level you may ignore, but 66 or even 33 kV people are considering it, but if it is 66 kV or above, you have to consider your shunt capacitance. But if the distribution side at 11 kV side, there is no need to consider for overhead distribution, overhead 11 kV distribution system, there is no need to consider your charging capacitance or shunt capacitance, right. But for cable you have to consider, even it is 11 kV also you have to consider, because their charging capacitance is quite I mean it has a significant value, right. You cannot ignore that, right. So these parameters are uniformly distributed throughout, but can be lumped for the purpose of analysis and approximate basis. Actually, transmission line, you have seen these parameters are uniformly distributed, right, but for our understanding and for our analysis, we will consider they can be lumped for the purpose of analysis and approximate basis. So, this way we will analyze. For example, let us start from the line resistance, right. So, generally the DC resistance of a solid round conductor is given by, we put RDC is equal to rho into L upon A. This is equation 1, because this is a second topic. So, this is again equation 1, right. Rho is equal to resistivity of the conductor, L is equal to length of the conductor, and A is equal to cross sectional area of the conductor, right. So, the conductor resistance is affected by 3 factors. One is the frequency, second is the spiraling, and third is the temperature. These 3 factors basically affects the conductor resistance, and this is basically a DC resistance. RDC is equal to rho into L by A, right. So, the DC resistance of a stranded conductor is greater than the value given by equation 1, because spiraling of actually if you look at that the transmission line conductors, they are actually your spiraling of the strands make them longer than the conductor itself. It is not a solid round conductor, it is conductor, but it is stranded conductor, right, and because of spiraling, that actual length is slightly longer than the conductor itself, right. This increase in resistance due to spiraling is around 1% for 3 strand conductors and about 2% for concentrically stranded conductors. So, little bit higher, but 1%, 2% is not that very high, but you have to consider. Now, when an alternating current flows through a conductor, the current distribution actually is not uniform, right. For DC current, the current distribution is uniform, right, over the conductor cross sectional area, and the degree of non-uniformity increases with increase in frequency. Actually, if it is a DC current, no, that suppose cross sectional area is say 5 centimeter square for a conductor, very large, of course, 5 centimeter square, and say 5 ampere current is flowing. So, current density will be 5 by 5, 1 ampere per centimeter square, and it is uniform for DC current, right. But when alternating current or AC current flows, right, through a conductor, the current distribution is not uniform, right, over the conductor cross sectional area, and the degree of non-uniformity increases, right, with increase in frequency, and this we will see later on when we will study this inductance, right. The current density is greatest at the surface of the conductor. This causes the AC resistance to be somewhat higher than the DC resistance, right, and this effect is called as skin effect. When we will study inductance, at that time we will see what is skin effect, right. That means at every point of that cross section, the current density is not uniform for your this thing when for a alternating current, right, current density is different. So, that means this shows that AC resistance is higher than the DC resistance, right. So, this effect actually is known as skin effect. So, the conductor resistance increases with the increase of the temperature. If you know that if temperature varies, then conductor resistance also will increase, right. For small changes in temperature, right, the resistance increases linearly as temperature increases. If temperature changes is small, the resistance will also increase your what you call linearly. So, and the resistance at a temperature T is given by, you know, this RT is equal to R0 1 plus alpha 0 into T, this is equation 2, where RT is equal to resistance at T degree Celsius. These are all basic thing, right, and R0 is equal to resistance at 0 degree Celsius, and alpha 0 is the temperature coefficient of resistance at 0 degree Celsius. So, by equation 2, by using equation 2, the resistance R2 at a temperature T2 degree Celsius can be found if the resistance R1 at a temperature T1 degree Celsius is known, that is that R2 upon R1, right, is equal to T2 plus 1 upon alpha 0 divided by T1 plus 1 upon alpha 0. That means if you know the resistance R2 at temperature T2 degree centigrade can be found if the resistance R2 can be found at your temperature T2 if the resistance R1 at temperature T1 if it is known to you. So, what we will do from this relation, we will write one equation R2 is equal to R0 plus 1 plus alpha 0 your T2, another one we will write R1 is equal to R0 1 plus alpha 0 T1, and if we divide, then you will get R2 upon R1 is equal to T2 plus 1 upon alpha 0 upon T1 plus 1 upon alpha 0, right. Now, this is that your what you call, this is the resistance, and although we will study everything slowly and slowly, and I believe that many of you have studied this inductance, capacitance, all these things, right. So, during this time, apart from, of course, next we will come to inductance, after that capacitance, and after that medium line, long line, short line. But before that, I am giving one exercise to all of you, and you try to do this. For example, this is an exercise for you, right. This is an exercise for you. Suppose you have all these things we will study, but in advance I am giving. Suppose you have a transmission line, this side is sending end, this voltage is say V1 angle delta 1, this side is receiving end, is sending end voltage V2 delta 2, right. This impedance of the line is R plus Jx, current flowing through this line is I, and here you have load P plus Jq. This is the load, right. Now, I am not writing anything, but from my recorded voice you can make out, right. Now, my objective is I want to maintain this V1 and V2, this is voltage magnitude, V2 voltage magnitude. I want to maintain my V1 must be equal to V2. I want to maintain that, for which I have to connect a shunt capacitor here, which is injecting that say QC, I put JQC, which is injecting a your what you call a reactive power here, right, to maintain voltage V1. Initially when it was not there, V2 was, let's say V2 was less than V1, it is a lagging load. So, V2 was less than V1, current is flowing in this direction. Now, as soon as I put some value QC here, I want to maintain V1 is equal to V2. Then I want to find out QC in terms of, I made function of in terms of V1, V2, P and Q. Delta has to be eliminated. There should not be any delta in mathematical expression. I want to find out QC must be function of V1, V2, P and Q, right. Only given hint is that your QC, when you will try to find out, it will be a quadratic equation of QC. There will be two solutions for QC, one is feasible and other is not feasible, but both the solution will be function of V1, V2, P and Q, but one is feasible, other is not feasible, right. So, this exercise I am giving you, and those who will take this course, this is an exercise. If you can do this of your own, I will solve it, but before that, before those video lecture when you will see, before that if anybody can do it and can show this to me, then I will appreciate that, right. So this is a very interesting problem. So